light was used by humanity for a very long time. You may have heard about a magic stone that Vikings used to determine the position of sun in a cloudy weather. Photographers know that if you want to achieve a deeper blue color of sky on a photo, you can put and adjust the polarizing filter on your object glass. The light reflected from the upper layers of the atmosphere is polarized. So with the polarizer, you can either enhance it or reduce it. The light which goes directly from the sun is not polarized. So by reducing the polarized light from the sky, you can determine the position of sun, even if it is hidden by the clouds. So what is light polarization? The wave theory of light describes light waves as transverse waves, which means that the direction of the wave oscillation is perpendicular to the direction of the wave propagation. This direction of oscillation is called the wave polarization. When we have light coming directly from sun, there are many waves polarized in different directions. So the whole light flux, in this case, does not have the preferred direction of oscillations, which means that the light is not polarized. However, when we have light which was reflected from some surface or some matter which partly polarizes it, like water surface, for example, then the majority of waves will have the same direction of oscillations, and the light becomes polarized. Now, if you want to determine the polarization of light, we still don't have anything better than that Vikings magic stone. Though, I suppose, more neat and clear and transparent. The thing I'm holding in my hand is called the linear polarizer. It is made of a thin slice of a crystal which has a very peculiar organization on the molecular level. Molecules of this crystal form dipoles, which are all aligned along the same axis or direction. When light polarized along this axis falls at a crystal, the dipoles begin to oscillate because light is an electromagnetic wave and it can push opposite charges to the opposite directions. This oscillation of charged particles produces the secondary wave, which interferes with the primary wave on the other side of the crystal and extinguishes it. This secondary wave goes in both directions. First, in the same direction as the primary wave, where both waves interfere to nothing on the other side of the crystal. And second, in the opposite direction, to that side of the crystal where the primary wave came from. This secondary wave, going to the opposite direction, is perceived by us as a reflected wave. And you may notice that this reflected wave is still polarized in the same direction as the primary wave, which is this direction of orientations of dipoles in the crystal. Good. Now, if the primary wave is polarized orthogonally to the axis of dipole's orientation, then it does not produce any oscillations of the dipoles. Thus, there is no secondary wave and no reflection. The wave just easily goes through the crystal. This direction, which is orthogonal to the line along which all dipoles are oriented, is called the optical axis of the crystal. The light polarized along this optical axis easily passes the crystal. The light oriented orthogonally to optical axis is fully reflected by the crystal. This is how actually the transparency and the reflection work. Materials that have something to oscillate on the frequency of the falling electromagnetic waves are more likely to produce secondary waves, which will extinguish the waves after the material and form the reflected waves. Okay, now what if the falling primary wave is oriented like this? It is not collinear to the optical axis and not orthogonal to it. And let's imagine that this wave is represented by just one photon, which means it cannot partly pass and partly reflect. It must either pass or reflect, since it is just one photon, and it cannot be divided in parts. Well, no surprise to us here, I hope. The result will be truly random. This photon passes the crystal with the probability P, and it reflects with the probability R. And both these probabilities are defined by the angle theta, which is the angle between the polarization and of the photon and the optical axis of the crystal. Another interesting result is that in the case of reflection, the reflected photon will have polarization orthogonal to the optical axis, while in the case of passing the crystal, the photon will have the polarization collinear to its optical axis. So interaction with the crystal alters the photon polarization. We can easily show this if we have two linear polarizers. Let me assemble them together. Okay, these are two polarizers, attached one after another. In the case when their optical axes are collinear, like here, we can see that the second polarizer does not reduce the light flux, since the photons coming from the first polarizer are already collinear to its optical axis, and they all come through. But if we rotate the second polarizer by a quarter of the circle, so that its optical axis is orthogonal now to the optical axis of the first polarizer, and you can see that the second polarizer reflects all the photons past the first polarizer, and nothing passes through. This state of two polarizers is often called crossed polarizers. So again, axes are collinear. You can see my eye here pretty clearly, and crossed. You can see my eye at all, but probably you can see the camera now. Okay, I don't want you to pay much attention to these probabilities and their calculation for now. The most important fact here is that we have a measurement process with exactly two possible random outcomes.